Welcome back, everybody. So I'm here on page 9 of the chapter 10 lecture note outline, which we are going to finish today. So you'll see on these last pages of the chapter 10 lecture note outline that we're going to be doing a few more gas law example problems. So treat these as sort of examples using the method of problem solving that I demonstrated during the last lesson, which is we look at the gas law problem and we see there really are two types. We see problems that involve a change in the conditions and problems that have static conditions or unchanging conditions. And in both cases, we can use the ideal gas law to arrive at a simple solution for these types of problems. So I'm going to work through a few of these problems. Most of the time, I'm just going to show the actual solution, the work to get to this solution, and then I'll interject here and there when I feel like there's an important note to mention, something to explain in more detail if necessary. But for the most part, I will keep quiet and just draw my solutions. So the best way to work through this part of the video is to pause before each of the problems and try to work through the solution yourself. And as I go, maybe unpause the video and look at how you're doing, how you're following along, if it's working out, and then you can check your answer at the end. Hopefully you're able to solve these problems easily using the types of methods that I show here. And then after that, what we're going to do is see the last part of the lesson is something called the kinetic molecular theory, which is just some sort of concepts about gases in general and the theories that explain them. So we'll go through that, and then the very last page you'll see, which is partial pressures, that actually I'm going to exclude from the unit actually. So we're going to not do that very, very last page on this. So that's basic intro to today's lesson. Let's get started. So the first thing I'm going to do is just write down some notes about what I'm seeing when I read through the problem. So for example, we're seeing here that there's an increase in the temperature and we're being asked what is the resulting change in the volume. Now remember that Charles' law expresses this relationship between temperature and volume. And we see that with an increase in temperature, we would expect an increase in volume. Again, that's Charles' law. Now let's work on our solution. What I'm going to do first is write down all the parameters that I'm given. With any missing parameters, I'll write a little question mark next to that. Also, just a quick note here, I put a decimal place next to 100 for the degrees Celsius. That way it makes it have 3 significant figures instead of the 1 that would be there without it. So now that we have all the parameters written down, let's look at how we can use the ideal gas law to help us solve this problem. So I'm showing here how we can rearrange the ideal gas law to solve for the constant R. And if we do that, we can see that P1V1 over N1T1 is equal to P2V2 over N2T2. So notice that the number of moles and the pressure remain constant while we only see a change in the volume and the temperature. Now because of this, we can cross out the pressure and the moles on both sides of this equation. This leaves us with the expression for Charles' law, which is V1 over T1 equals V2 over T2. Now what we're looking for is a solution for V2, the new volume after the change. We can rearrange this equation to solve for V2 by noting that V1 times T2 divided by T1 would be equal to V2. Now all we need to do is plug in the values for the initial volume, the final temperature, and the initial temperature into this expression. Now don't forget we have to convert degrees Celsius into Kelvin, which I've shown here on the left with significant figures analysis. After we plug all of this in, we get our final value of 1.94 liters. And that makes sense because we were expecting an increase in the volume. The initial volume was 1.55 liters, the final volume is 1.94 liters, and that agrees with Charles' law. All right, so that's the first example. Let's go take a look at the next one. All right, so in this next example, we're told that a confined quantity of gas is at a pressure of 2.50 atmospheres. That would be our initial pressure. The initial temperature is given as minus 22 degrees C. And we're being asked, what is the pressure if the temperature increases to positive 22 degrees Celsius? So what I want you to do is try to address the two questions I have listed here, which is the first, what gas law best applies to this problem. Right, now we're looking at a change in the pressure and the temperature. So we're looking at the relationship of temperature and pressure change in the absence of any other changes. What law is that? So try to figure that out and then show your solution. So what I want you to do is pause the video and go through the same step-by-step procedure that I showed in the previous problem. Start by writing out the different parameters that you're provided, show any missing parameters with a little question mark next to it, and then use the ideal gas law to try to cancel out the constant values. So when you're ready to look at the solution, here's what it looks like. Notice here I've already started converting the temperatures from degrees Celsius into Kelvin so that I can use them in my solution. Notice also that we're missing the final pressure. That's what we're looking for here. So whatever we end up with at the end, we're going to have to solve for P2. All right, let's see how we go about doing that. So we're told that there's an increase in the temperature and we need to find out what is the resulting change in the pressure. Recall that temperature is directly proportional to pressure, so if one goes up, the other goes up. This is an example of Gay-Lussac's law. Now let's go about using the ideal gas law to see how we can arrive at a solution for the final pressure. So looking at the ideal gas law, we can rearrange it to solve for R, and then we recognize that initial conditions would be equal to final conditions. Now, what we need to recognize also are the constants here. We have the number of moles, N, and the volume as constants. That means we can cross these out on both sides of the ideal gas law. And what we're left with is P1 over T1 equals P2 over T2. You might recognize this as an expression of Gay-Lussac's law, which we just derived from the ideal gas law. Now what we need to do next is solve for P2. That's our missing parameter. So we're going to multiply both sides of this equation by the final temperature, or T2, and we'll be left with a solution for P2. Let's see how that works. So P2 would be equal to P1 times T2 over T1, and then we need to plug in the values for the initial pressure times the final temperature divided by the initial temperature. And if we do that, we get 2.94 atmospheres. That's with 3 significant figures. All right, so that's the second example. Let's go to the next page and look at a few more. Let's read through this problem together. It says, a quantity of a gas has a volume of 17.5 liters at a pressure of 6.00 atmospheres and a temperature of 100 degrees Celsius. What is its volume at STP? Now recall I mentioned this thing called standard temperature and pressure a few lessons ago. Standard temperature and pressure is defined as 0 degrees Celsius at 1 atmosphere. And when we're at standard temperature and pressure, we can also define the molar volume of any gas. Specifically, at standard temperature and pressure, 1 mole of a gas, any gas, will have the volume of 22.4 liters. This is defined as the molar volume of a gas at standard temperature and pressure. So from this, we can actually develop a conversion factor that allows us to convert between volume and moles as long as we're at standard temperature and pressure. It looks something like this. Suppose you determined how many moles of a gas there were and you knew that that gas was at standard temperature and pressure. Determining the volume of that gas would be as simple as multiplying by this conversion factor, where we have 22.4 liters per mole. That's because we're at standard temperature and pressure. So this would give us the volume of the gas at STP. Now, all it is a matter of finding the number of moles. So let's see how we can do that for this problem. First, let's write down our parameters for pressure, volume, moles, and temperature. Notice that we're missing N, the number of moles. Also notice that our temperature is in degrees Celsius rather than Kelvin. We're going to need to convert that into Kelvin. So now our task is to solve the ideal gas law for the missing number of moles, N. So we write out the ideal gas law, identify N, and then we isolate N by dividing by RT. If we plug in the values into this equation, pressure, volume, R, and temperature, we can solve this as 3.4274 moles of gas. We then plug that value into our conversion up here and convert into volume, which we get 76.8 liters for. So let's just recap what we did there. We first wrote down the parameters that we were provided with, noting that n, the number of moles, was the missing parameter. We then took the ideal gas law, and we isolated that missing parameter n by dividing both sides by RT. We're left with the n is equal to PV over RT. We then plugged in the value for pressure, volume, R, which is a constant, and temperature. That equals 3.4274. That's moles of gas, N. You can actually confirm that that's the correct unit by doing a quick unit analysis on this expression. So notice first of all that we cancel atmospheres in the pressure. That's because we're dividing by R, which has atmospheres in the top part of that unit system. So atmospheres divided by atmospheres, it cancels atmospheres in both cases. We're also canceling out Kelvin because we have temperature in units of Kelvin here, crossing with the bottom unit of R, Kelvin, over here. We're also canceling liters by noting that liters is up here and liters is here. So we're dividing liters into liters, which cancels it. Now we're left with the 1 over moles, or the inverse of moles, which happens to just turn out to be moles. So that's the unit for our result. And then we take that, the moles of the gas, which by the way has 3 significant figures, but we plug all of the values in and round at the end into this, and then we convert using the molar volume of a gas conversion factor. So we have moles of a gas here multiplied by 22.4 liters divided by 1 mole, and that gives us our 76.8 liters. Now again, this has 3 significant figures down here, which I've carried over from all of these parameters, and then I've rounded to 3 significant figures at the end. All right, so that's that example with the molar volume of a gas at STP. Just really important to remember that 22.4 conversion factor there. That's a nice one. So let's go to the next example, which reads, what mass of neon is contained in a large neon light if the volume is 3.50 liters, the pressure is 1.15 atmospheres, and the temperature is 23 degrees Celsius? So notice, first of all, that there aren't any changes to the conditions in this problem, right? We're just given a series of parameters, and none of them change. So to solve this problem, let's just first start by writing down all of the parameters that we're given and seeing what we're missing, and then figure out the best way to solve it from there. So reading through it, it looks like we are given the volume, which is 3.50 liters, the pressure, which is 1.15 atmospheres, and the temperature, which is 23 degrees Celsius. Notice that we are not given the number of moles. That would be N. So let's write N equals question mark. That's what we're going to be solving for. Also notice that the temperature is given to us in degrees Celsius. So of course we need to first convert that into Kelvin. So notice that we're missing N, the number of moles. How are we going to actually figure out what N is? Well, that's right, we're going to solve the ideal gas law for N. So recall, the ideal gas law is PV equals nRT, and all we have to do is divide both sides by RT in order to isolate the variable N. Now that we see that it's PV over RT is equal to N, we can just solve for N by plugging in the values of pressure, volume, the constant R, and temperature into this equation, and then solving for N. So our value for P, for pressure, is 1.15 atmospheres. Our value for volume is 3.50 liters, and R, which is the ideal gas constant, is 0.0821, and that's in units of liters times atmospheres over moles times Kelvin. Finally, we need the value for temperature, and because we're using this value of R with these units, we need to convert that degree Celsius into Kelvin, which I've shown here. We have 296.15 Kelvin. So once we plug all of these values in, the next thing we can do is actually look at the unit analysis for it. Let's figure out which units are canceling by noting which ones are dividing into other units. If we have a unit that is in the numerator being divided by a unit in the denominator, that unit would cancel, of course. So notice here we have liters being divided into liters. We also have atmospheres being divided into atmospheres. we also have this relationship here between Kelvin. We're dividing this Kelvin into this Kelvin. So those units of Kelvin are also eliminated. And what we're left with is the only unit left is this mole, which is at the denominator of that R value. So if we looked at the units for this expression, all of the units on the top go away. So it becomes unity, or 1. And those are being divided by all of the units on the bottom, which have all been eliminated except for 1 over mole. Now the inverse of mole is mole. So that's what we're left here with, is the unit of mole. So after we go about doing the calculation, we get 0.16554 moles of neon. Now, we're not being asked in this problem to provide the moles of neon. We're being asked, what is the mass of the neon? Now, we have the moles of the neon. We can definitely convert that into the mass. All we have to do is use the molar mass as a conversion factor. So what we'll do is we'll start by writing out our moles of neon, and then using the conversion factor of molar mass, we can convert that into grams of neon. So the molar mass conversion factor, again, allows us to convert between moles and mass. So we can go from moles to mass or mass to moles. And we get this value off of the periodic table. So if you go look at the periodic table for neon, you will find the atomic mass is given as 20.180. That's grams per mole. Now we can go about doing the calculation here, but what about the significant figures? So I'm showing on the parameters the 3 significant figures in the volume, the pressure, and the temperature. Now you might say, well, hey, the temperature only has 2 significant figures. But remember, to convert it into Kelvin, we had to do an addition problem. Now this adds some significant figures because of the value for Kelvin that we're adding into it. In the end, though, we get 3 significant figures, and the calculated result, rounded to the correct number of digits, is 3.34 grams, and that's grams of neon. Okay, so now we're going to turn to the next page, which is page 11 of the Chapter 10 lecture note outline. We're going to go over the kinetic molecular theory of gases, and then on page 12, we're going to see the partial pressures page. We're going to actually cross that one out, so the next page will actually be the last one for this lesson. Let's go take a look. So on this page, we're going to learn about a theory called the kinetic molecular theory of gases. Essentially, this theory seeks to explain the properties of gases that we observe through some simple theoretical explanations about what the particles are doing at a molecular level and how those molecular level events explain at the macro level what we actually observe for gases. So let's actually start by reviewing the properties of gases. Then let's look at the different proposed tenets that the kinetic molecular theory presents and see how those might explain at the macro level the properties that we observe for gases. So the properties that we know about gases is, first of all, they are compressible. So we can take a gas and we can change its volume significantly. So for example, we can have a gas inside of a small canister that we then allow to fill a number of balloons, and the volume of those balloons could be several thousand times the volume in the canister. So that means we've taken the gas that has a much larger volume and we've squeezed it into a much smaller space. That's because gases are compressible. We can change their volume significantly. Another property that we know about gases is that they have a low density. What that means is there's very little mass per unit volume. Right? This is unlike solids and liquids, which have a lot of mass in a relatively small volume. By comparison, gases have the opposite situation, very low density. Now, to show you an example of this, I like to show this in class actually when we're face-to-face. But if you take a piece of dry ice, you can put it inside of a balloon, and that little piece of dry ice starts to sublime. So it goes from the solid state, right? Dry ice is solid CO2. And it sublimes. It goes from that solid state of CO2 into the gas state of CO2. And we see that as a gas, it has a much larger volume than it does as a solid. And that's because as a gas, that same amount has a much lower density. So as it converts into a gas, its volume expands because its density decreases. So after 10 minutes, we see the balloon is much larger than it was at the beginning. Now, eventually, of course, this balloon explodes. It's kind of a fun little demonstration because everyone jumps. No one knows when it's going to explode, but it does, and it's always a lot of fun to see everybody jump. This is an example of the density difference between solids and gases, and liquids are the same way. You can imagine that if you take a liquid and you boil it and you collect its vapors as a gas, it has a much larger volume. This is why you never want to boil a liquid inside of a tightly sealed container, right? If you've ever done anything with like a pressure cooker, you'll see that when you try to contain a hot liquid inside of a container that has a fixed volume where the volume can't expand, you need an incredibly strong piece of equipment. So pressure cookers do this by creating a system of locking steel where the volume can't expand, and it has a pressure release valve so it doesn't actually explode. Anyhow, that's low density of gases. Another property of gases is that they mix completely. So if you take a gas and you put it inside of a container, it will mix with any other gas inside of that container very efficiently. They will not remain in separate places. Now, this isn't true with solids and liquids, right? So if you take some sugar and you put it inside of a glass of water, basically that sugar is going to sit there for a very long time. It will eventually dissolve, but it won't mix completely. You can also see this when you take two different liquids. It's possible, actually, to very carefully pour two different liquids with different densities so that one is on top of the other and that they don't mix. Now, it turns out that with gases, this is not possible. The gases mix on their own. No additional energy is required. And we're going to look at the kinetic molecular theory to try to explain why that is. It's a very interesting property of gases. And finally, we know that gases also take on the shape of their container. So these are the properties of gases. Let's see what the kinetic molecular theory does to try to explain some of this. So let's talk about the first tenet of the kinetic molecular theory, which is that a gas is composed of very small particles, which are moving at a very high velocity. And also, just to reiterate, when I say very small, I mean incredibly small. In fact, the kinetic molecular theory describes an ideal gas where the particles have zero volume. So they're incredibly small, and the smaller the particles, the more ideal the gas is, or the more it obeys the ideal gas law. The larger the particles, the less ideal the gas. So these are the first two parts of this first tenet. It's that the gas particles are very small and they are moving at a very high velocity. What does this explain about gases? Well, I think it would be fair to say that this tenet would explain both the compressibility that we see for gases, as well as the way that gases mix efficiently. How does it explain the fact that gases mix completely, whereas solids and liquids don't? Well, imagine if the particles are moving very fast. If you have two gases in the same container and the particles are moving very quickly, that means the particles will pass one another. And that's mixing, right? The particle of gas A and the particle of gas B will pass each other in the container, and then you'll have a random distribution of the different particles. Therefore, you get complete mixing. Now, what about the compressibility? I think that one's a little bit more difficult to get out of this, but if you think about the volume of a particle, right? Now, if we have a very, very small particle, that means all the other particles are small, and therefore we can have a lot of space in between those particles. You can also think about the speed of the particles. If they're moving very quickly, that means the distance between them is probably large because they're moving very fast. This means both of these together mean that there's a lot of space between the particles. And if there's a lot of space between the particles, that means we can push them closer together at some point. That's compressibility. Okay, let's look at the next one. The next one, number 2, says, gas particles are in constant motion, exerting pressure, which is force over area, on the sides of the container through collisions. And it should say also collisions with the sides of the container. So what does that explain about gases? Well, remember that gases take on the shape of their container. And this tenet is a pretty good explanation of why that is. Now, if gas particles are in constant motion, exerting pressure on the sides of the container, that means that they will expand to fill the container they're in. They will basically explore to the boundaries of the container. And therefore, they will take the shape of their container because the particles are always moving, bouncing off the sides of the container. Now, what about number 3? It says all gas collisions are highly, in quotes, elastic. Now, what does elastic mean? So to give you an example of an elastic collision, I'm going to show you these two basketballs colliding with one another. Now, if these two basketballs collided in real life, as you would expect, they would bounce off of each other. This is called an elastic collision. It's called an elastic collision because all of the kinetic energy that is involved is conserved. So each ball has its own kinetic energy as they move towards one another. When they collide, that kinetic energy is transferred, and each of the basketballs reverses direction, carrying with it the kinetic energy that was given to it by the other ball. This is called an elastic collision because there's no loss of kinetic energy. Now, in reality, when two basketballs collide with one another, there is some kinetic energy that is lost, right? There's the sound, there's the heat. All of this kinetic energy is actually lost in the system. So if these two basketballs were actually colliding, eventually they would hit each other, and then they would eventually slow down and they would stop moving eventually. And this is because the collisions are not perfectly elastic. They're pretty elastic, but there's a little bit of inelasticity in those collisions. So what is an inelastic collision then? Well, an inelastic collision is the exact opposite. In this diagram, you can see the example of the perfectly inelastic collision, where the two masses are moving forward with their own initial kinetic energies. When they collide, instead of actually bouncing off each other, as they did in the elastic collision, and they travel in opposite directions, in the inelastic collision, they collide, and then the masses join together. The combined masses then continue traveling in a direction with a velocity that relates back to the masses and the velocities of the particles which collided. A good example of this would be like if a bug hit your windshield when you're driving, right? Each of the particles, one is the car, the other is the bug, have their own individual masses and velocities, and they collide, and then the combined mass travels forward in a direction that's largely determined by the larger mass that has a much higher momentum because of that mass. So they continue in the direction that the car was going rather than the direction that the bug was going. Now, what does this elasticity of collisions actually explain about what we observe with gases? Well, another observation we have with gases is that their volumes are stable over time. So you can fill a balloon up with gas, and if that balloon doesn't leak, the volume will stay consistent over time. Now, if gas collisions were not elastic, we would not expect the volumes to stay the same over time, and that's because there would be a loss in kinetic energy every time the gas particles collided. And because they're in constant motion, we would expect relatively large amount of collisions over time. So because the gas volumes are stable, we can assume that the gas collisions are highly elastic. Now, the next point number 4, says that the forces of attraction and repulsion between individual particles in the gas are negligible. Now, what does that explain about what we see with gases? Well, we know that gases are compressible, and this helps to explain that. Right? If the forces of attraction and repulsion between the particles of a gas were not negligible, they were significant, we would not expect the particles to be far apart from one another for very long. If the particles attracted one another, they would all get close together and things would clump up, and we wouldn't be able to have all the space in between those particles. And therefore, gases would not be compressible for very long. Okay, number 5. Temperature is a measure of the kinetic energy of the gas. So if temperature is a measure of the kinetic energy of a gas, and we know that kinetic energy is equal to 1/2 times the mass times the square of the velocity, that means that the temperature is basically related to this mass times the square of the velocity. Now, of course, because we have a fixed mass, that mass is constant, right? We're not changing the mass of an atom. It stays the same. That means that when we change the temperature, that must mean the velocity is also changing. So if we increase the temperature of a gas, we're increasing its kinetic energy and therefore also increasing its velocity. It means when we increase the velocity, we must also be increasing the collisions that the particle is having with the other particles and also the walls of the container. And the increase in collisions will therefore mean an increase in the pressure or an increase in the volume. Really what I'm saying here is that this tenet of the kinetic molecular theory explains both the direct proportionality between pressure and temperature, and volume and temperature. So this explains two of those individual gas laws that we saw earlier, namely that Boyle's law states that volume is directly proportional to temperature, and Gay-Lussac's law says that pressure is directly proportional to temperature as well. So that's a basic overview of the kinetic molecular theory. Let's go look at the last page where it's about partial pressures. We're actually not gonna go through that page, but I'll just kind of wrap things up on that last page in the lecture notes. So here on page 12 of the lecture note outline, we have it looks like part 6 here, which is Dalton's law of partial pressures. It's interesting stuff, but we're not going to actually spend any time working on it. We don't need to do that this semester. So we're going to skip this page in the chapter 10 lecture note outline. So this is going to wrap up this lesson today. I would definitely suggest practicing some of the other gas law problems that I have available on Canvas on the problem sets. Please let me know if you have any questions about that or anything else, and I hope you're doing well. Take care.